Okay, so the way that you'll know that you're going to do this special procedure, different than regular redox, it's still a redox reaction, but you'll recognize that you have to do something different because it will specifically say in acidic solution, or an acidified solution, or a basic solution of blank blank reacts with blank blank. So you're going to know because it says an acid or a base is involved. The other way you'll know is that it's impossible to balance. Impossible to balance without this special procedure that I'm going to give you. Thinking? Okay, the first thing that we're going to look at is acids. In the general sense, if I'm using an acid so far before today's lecture, if I say acid, you say H+. So on your quiz just now, you saw something that had acid in there, right? You should have written H+. That's true for all strong acids except for nitric acid. So if I say nitric acid now, you don't write H+. The H+ is not strong enough to do any sort of reaction with something else. So the H+ will not get reduced like it did in the last case. We would go from H+ to H2. So instead, we're going to use the nitrate. So when you hear me say HNO3, which is nitric acid, oops, I'm writing nitrate, nitric acid, that means that you write NO3 minus, okay? All other acids, strong acids that we use, we're going to write H+. So you're going to write nitrate instead of the H+. So the nitrate itself will oxidize metals that H+ cannot. So an oxidation of a metal. So let's look at all our oxidation numbers. We have a -2 times 3 is -6. So nitrogen would be a +5. And then this is 0 because it's in elemental form. So we're not going to make a metal go to a negative charge, correct? So clearly that one has to get oxidized to some positive state, which means that the nitrate has to be what? Oxidized or reduced? What did I do to the metal? I oxidized it. So what do I have to do to this? I have to reduce it. I can't reduce an oxygen to a -3 or 4 or anything other than -2. So obviously I have to reduce the nitrogen. So you reduce the nitrogen to make it NO. In a very concentrated nitric acid solutions, so concentrated nitric acid, you could also produce NO2 as an option. I don't know that they would ever give that to you, but it would say clearly a concentrated solution of nitric acid versus just regular nitric acid. So I don't care that you memorize this piece. What I care about is that you memorize that if you get NO3 minus, that you write the half reaction NO. All right, so that's the first half reaction that you need to memorize for an acid. So I wrote that down there on that note card. Okay, so here's an example using the nitric acid. A solid copper penny, so if I say solid copper, you write Cu solid, is placed in a solution of nitric acid. Well, now instead of saying H+, you write NO3 minus, right? So Cu solid plus NO3 minus, you memorize the half reaction, NO3 goes to NO, and then this is obviously your other choice for oxidation. What's one more choice that you could have written here? +1, right? Because copper has a +1, +2 oxidation state. So you could have oxidized it to go to a 1 or a 2. All right, now check this out. If you were to balance this on my test, you would say copper has 1, copper has 1. Nitrogen has 1, nitrogen has 1. And then you get to the oxygen, and it's impossible to balance. Because if I put a 3 here, then I have to put a 3 here. Well, then that makes 9 here, and then I put a 9 here. Do you see that this never will be balanced? Agreed? So that's another clue that you have to do this special procedure. So the special procedure I just printed up those extra slides for you, is this special half reaction method. That's what is on your printout right now. The only thing I added here is a number 8 because later in these slides you're going to see that if we have a basic solution, we still follow the same steps, but we do one more step if it's a base. So for right now, we're just going to focus on the acid ones. It's not really worth me explaining this too much. I'll read it to you, but you still do the same half reaction method that I taught you. So you write one of your reactants in an arrow and your other reactant in an arrow. You choose which one's getting oxidized and reduced. Then you follow the steps. So balance all of your atoms first. This one's a key one. If any mistakes are made, it's usually because you don't balance your atoms. So if I have like 1 manganese on one side and 2 manganeses on the other side, you have to put a coefficient of a 2 to balance your atoms. So I would say this is the one spot where students ignore. They do the rest of the steps, but then they'll get it wrong because they forgot step 1. Okay, so we're going to skip through this, but we're just going to try it directly looking at your notes. So if this is the reaction, we're going to follow our steps. First step is to write, right now it says the reduction half-reaction. So what's the reduction half-reaction looking at this reaction? Cu going to Cu plus 2 or NO3 minus going to NO? NO3 minus, so write that down. That's step 1. Write your half-reaction. What's step 2? Look at your sheet. Balance what? Balance all atoms except for oxygens and hydrogens. So are your nitrogens balanced? Yeah, that's step 2. Nitrogen is already balanced, so we're okay. So now we need to go to step 3. Balance for oxygen by adding H2O. If you add H2O, how many oxygens are there? 1. So you're going to add however many oxygens you need, you have to add that many waters. When you want to balance oxygen, you add water. You can't just add oxygen. So how many oxygens are on the left side? 3, and how many are here? How many more do I need? So how many waters do I add? 2 H2O. So the next step is you add 2 H2O to the right side. There it is. Right? Make sure the coefficient of 2 is in front of that because you need to make sure that you have enough oxygens. All right. How do I balance now for hydrogen? Add H+. Okay, so as soon as we add water, we're introducing hydrogen, so we need to balance for that also. How many hydrogens are here? 4. So how many H pluses do I add to the left? Add 4 H pluses to the left. Plus 4 H plus. All right, what's your last step? Number 5, essentially. Balance the charge by adding electrons. Can someone grab that door? Thank you. So count up your charges. This has 1 with a negative, so that's a -1. This is a 4 with a positive, so that's a +4. What's the charge on the left side? +3, right? So this whole side is +3. What's the charge on this side? Jake? Is there a charge here? No? Are you looking at that? I was too earlier. I said the same thing. It's just a fleck on my board. Is there any charge? 0. Is there any charge? 0. So the whole side is 0. There's no charge, right? So how do I get rid of this charge? How many electrons do I need to add? 3 electrons. Electrons are negative, so they take away positive charge. So if I add 3 electrons to the left side, then I did this right. The other way to check that you're doing this sort of right is I know that I'm writing the reduction out, so electrons need to be gained, don't they? And gaining means the left side. If you accidentally did this wrong and somehow your electrons were on the right side, you would know you did something wrong. Because you have to be reduction, which means gaining electrons. So step 5, add 3 electrons to the left. Go ahead and jot that down.
I was going to say.
So next step is to write your second redox reaction. So now you're going to write the oxidation redox reaction. So your oxidation is what? Copper. So it's Cu goes to Cu plus 2. Step 1, balance for atoms. Are your atoms balanced, meaning copper? Yep. Are there any oxygens? Nope. Are there any hydrogens? Nope. So this is it. All we have to do is just like our simple redox procedure that we did anyway before this lecture. So you're just going to add electrons to which side? Yeah, 2 reasons. It's oxidation, so you have to give them up. They have to be on the right side. And then the other reason is that this is a 0 on this side, and this is a +2 on this side. So how many electrons are you going to add to the right? 2. So you go ahead and add them. So obviously when you're doing this with your own work, you're not going to write out this reaction 4 times, right? You're just doing the steps mentally with me right now, but you would literally just write these 2 things and then you're done with it. Until you have to combine them. So now that we're going to combine them, we have to check for electrons. So just like you did in the last 2 lectures, you have to balance your electrons. So now you're going to multiply to find the least common multiple of each of them. So here's your reduction half-reaction, here's your oxidation half-reaction. What do you need to multiply this by? What do you need to multiply this by? 2, 3. So go ahead and do it, combine them, and write out the total reaction that's left. Everybody good there? So the last step, number 7, is to add your half reactions and cancel things that are the same. So obviously the one thing that needs to be the same are your electrons because you have to cancel them. Electrons don't appear in any final reaction that you've written. But I want to point something out to you before we look at the next slide. You will sometimes get reactions where you have some water on the left and then you have some water on the right. And so say I had 6 waters on the left and 4 waters on the right, what do? You cancel, and how many waters should be left? You guys have to go back to 1st grade. 2. No 3, just 2. Like if I had 6 on the left and 4 on the right, the 4 waters would cancel with the other 4 waters because they're literally molecules. We're counting them up as the coefficient. There'd be 2 waters left on the left. Got it? All right, but that's not going to happen in our case. So all we're looking to do is cancel our electrons and combine everything that's the same. And so you cancel electrons, and here's our final reaction. And then you need to check. So most students will do this whole thing, and then either they forget to check, or they'll check and they realize they did something wrong, which is okay. I realize that this is a very long procedure and process, but it's sort of just, it's really not chemistry. It's not like your brain has to crunch to figure stuff out. It's just a process. So if you got it wrong, you just erase your work and try it again. So how do you know you got it wrong? You check. 2 nitrogens, 2 nitrogens. 6 oxygens, 2 plus 4 is 6 oxygens. 3 coppers, 3 coppers. 8 hydrogens, 8 hydrogens. Okay, then what do you check? Charge. So 2 times -1 is how many? Anything here? Can you guys all look up here? Everybody's eyes up here. This is the one spot where students mess up on charges. You forget to multiply by coefficients. So 2 times a negative is -2. Anything here? No, 0. What is this? +8. What's the total charge on the left side? +6, right? That's the total charge of this whole thing. What's this? 0. What's this? +6. What's this? So the whole side is +6. Did we do it right? If you don't check that, then you're not sure if you did it right or wrong. All right, these are very likely going to be multiple choice questions. They will definitely be on your free response. I am 100% telling you right now, I'm giving you balance one of these redox reactions in acid. You're definitely getting one of them. But I also give these as multiple choice because the AP exam does this. They will give you this entire thing, and then the multiple choice question will say, how many electrons are transferred? How many electrons were transferred in this? You just did it through the half reactions. 6, right? But say you didn't want to go through the whole process of half reactions and balancing them and finding electrons. Did you just see how we could figure out that it's also +6? You just counted the charge on the left and the right, and then you had +6 on both sides. That's 6 electrons were transferred. Do you get that? The other thing that we do on the multiple choice is I leave out all the coefficients. And I give you the final reaction, but then I ask you to balance it. So I'll show you later on when we do more of these how to do that. You could always just go to the half reaction method, or you could attempt to balance it for charge, and that's usually where it'll work out best. All right, so that's the whole procedure. If you follow the steps and you practice it a lot, and then it's just going to be sort of second nature when you see these to do it this way. All right, the next part here is what do you do when you have certain types of reduction reactions. So you're going to memorize these. These reactions are when you see the phrase in acidic solution or acidified. right? Everything that you took your quiz on today, nothing said acidified. It just was the only thing that had an acid was a metal is dropped in acid. You'll know this is different because it's going to be either nitric acid or it will say acidified solutions of, and that's how you'll know that you're going to use these. You're going to memorize. If it's nitrate, this is not going to say nitrate though. It's going to say nitric acid, right? That's what your verbiage will say. It'll say nitric acid reacts with maybe sodium sulfite, and then you're going to solve. So if it says nitric acid, you write this, and then you memorize that this is the reduction of it. This one, permanganate. Permanganate gets reduced. It's a minus 2 times 4 is a minus 8. Manganese is a plus 7. It goes to a plus 2C. You're just going to memorize it. So how will this one appear? It will be something like a group 1A plus the word permanganate. Permanganate, I think that's how you spell it. And then you'll figure out the reduction of it. You'll memorize it. Right? Because it's not going to say just, hey, here's the formula for permanganate. It's going to say potassium permanganate reacts with, and then it'll give you another oxidation reaction to memorize. Okay? The next one, this is dichromate. It's not going to tell you dichromate's formula. It's not going to just give you dichromate. It's going to be a group 1A plus dichromate. And you have to memorize the word dichromate is this, and this is the reduction of it. This was a minus 7. It goes to a minus 14. What must chromium be? Plus 6, because plus 6 would give me a plus 12, plus 12 minus 14 gives me the negative 2. Those are other questions I ask on multiple choice. I'll say, here's the reduction of dichromate. What was the original oxidation number in dichromate, of chromium in dichromate, right? You have to recognize that was a plus 6. That's simple. So it's a group 1A plus dichromate, and then it gives you this. So these are the 3 reductions that you're going to memorize. Got it? So if they are reductions, then what will the other piece be called? Oxidations. The ones that these oxidize are P block and D block metals. All right, so let's look at P block and D block. Pick a periodic table. P block, likely tin and lead, right? So if I'm going to oxidize tin and lead, what are those going to go to? Plus 2, plus 4, right? And then it says D block metals, so likely choices of that are iron, cobalt, nickel, copper, silver, zinc, right? We know all those charges. You have to know your charges in order to do these. So iron is 2, 3, 2, 3, 2, 3, copper 1, 2, right? You follow how I do that. The other choices, though, so those you know, the other choices to be oxidized are sulfite ions, peroxide ions, and substances that have a lower positive oxidation state than usual in acidic solutions. That one's a little tricky. The sulfite and the peroxide, you're just going to memorize. Those are up there also. I made that note card for you. So you'll get these, like, for example, potassium permanganate is in an acidified solution with, and then I'll just stick it with another group 1A, like sodium sulfite. So you know not to use potassium, you know not to use sodium, and you're going to memorize permanganate and you're going to memorize sulfite. So let's look at those. The oxidation of sulfite. It goes from a plus 4, because this is a minus 2, minus 6, plus 4, minus 2, minus 8, plus 6. So it oxidizes. So you're going to memorize that. Sulfite goes to sulfate. Again, it won't say sulfite, but it'll give you a group 1A with sulfite, so like sodium sulfite. Oxidation of hydrogen peroxide. The oxidation number on oxygen increases from a negative 1 to a 0. We know that peroxide is O2 minus 2, so it's a negative 1 here, right? So it's from on here, your oxygen's a negative 1 going to 0. All right, this substances with lower, less positive oxidation states has to do with this. There's a few of them. Carbon again. Mike, what does carbon want to be? So if I give you oxalate, oxalate is in a plus 2 state in this case, I think. Right? Did I do that wrong? Yeah, minus 2, minus 8, So carbon's in a +3 state. I was wrong, right? Because that would be +6. And that would give you the -2. Carbon wants to be a +4, so how do we make it a +4? We make carbon dioxide. You have to memorize that this is oxalate. So again, it'll say like sodium oxalate, potassium oxalate. So you're going to memorize that oxalate becomes the CO2. And then the last kind is basically when you have a choice. So you can, in this case, oxidize the chloride ion. I didn't tell you that chloride is a spectator ion. You can't just eliminate it. Sometimes it is a spectator ion, but you're going to see in a few examples that it is an option for oxidation. So if I can possibly oxidize this, it's a choice. Cl- could be oxidized to 0 oxidation state, right? So it's a choice for oxidation. This is possibly going to happen. However, if it's with a metal, so if this is a solution, it will make Sn+2 and it will make Cl-. I can oxidize this to what? Sn+4, right? I can make an Sn+2 become an Sn+4. I could also make a Cl- become a Cl2, correct? These both are choices for oxidation. So when you get stuck and you have to make a choice, this is why this slide is so important. The metal is always the correct one. If you have a choice, the metal gets oxidized. If you have a choice, the metal gets oxidized. You don't treat the non-metal. Even though it's a possible oxidation, you just don't use it. The metal is going to get oxidized. All right, so we're going to stop there, and tomorrow we're going to retry these. What I need you to do, you have like a minute, is I need you to write down those half reactions and memorize them, make note cards tonight. So I wrote them on my sheet like this, acid reductions, and I wrote them, acid oxidations, and then you're going to write them, or you're going to take a picture right now of those, and you're going to make note cards out of them. Bye, guys. Oxidations. Hold on one second. Wait. I'm recording it. Acid reductions. All right, so this slide says if you have a choice between the metal and the non-metal being oxidized, what do you choose? The metal is always oxidized. What are you looking for? All right, so let's look at the redox reactions in acidic solutions. Oh, first, before we go through this, hold up your note cards so I can see that you did what I asked you to do yesterday. So you're going to have those on your desk while we're trying these. Hold them up. And then I also want this on your desk while we're trying these today. Oh, good. I appreciate the ripped papers, even the ones during lunch. I like those too. Girls that were absent, we're just going to keep this on our desk, and then you're also going to make note cards. Those didn't print correctly, did they? Okay. When you read this, what do you see that tells you you need to use my special procedure? Acidic solution. Okay, what's another clue? A base, yeah, that's true. Acidic or base, acidified or base. But the permanganate, right? There's no other time I'm going to give you permanganate except it's in these special ones. So that's a clue. Okay, I'm going to have to do something with the special procedure, and I'm probably going to have to use a note card. So you have to decide your half reactions, oxidation or reduction. So here are our choices. An acidic solution containing tin 2 chloride. If it's a solution, you use ions. On the quiz that I gave you, if I gave you a solution of something and you wrote it as a compound, that's incorrect. Solutions have ions, right? So right now, you probably would read this and you'd say, I don't know what I'm supposed to do with that. So I would just leave it alone personally if I were you. I would go to the thing that I know how to do. You know how to handle permanganate, right? Is potassium involved? No, because it's a group 1A, and we don't involve group 1As. So I'm going to take permanganate. And because it's an acidified solution, I'm going to, I got to put it over here so it's in the video. Because it's an acidified solution, it goes to what? Mn plus 2. Okay, is this a reduction or an oxidation? You're guessing, right? How do you tell if something's a reduction or an oxidation? There's a way. You did it in lecture 1, the simplest way. Oxidation numbers, you guys have to know that. Oxidation numbers tell you which is oxidized and which is reduced. Do you agree? Okay, so we're gonna use this, and then we're gonna use one more thing later when I'm talking about it. So check your charges, -2, -8, +7, +2. Elisa, was that oxidized or reduced? Manganese. It is. Read this sentence out loud.
Oxidation number tell you which.
Is. All right, I didn't write a great sentence. Oxidation numbers tell you which is oxidized and which is reduced. All right, there's no O over there, so ignore it. What's the oxidation number on manganese?
2.
No, honey. Oh, you can't see my handwriting? That's a +7. Do you know that? Do you know, though, that it's a +7, even if you misread my handwriting? Do you understand that that's a +7?
Yeah, but I was.
You thought I wrote down 2. Okay. Yeah. So -2, -8. That doesn't even look like an 8. This is a negative, so this is a +7. So it went to a +2. Is this an oxidation or reduction?
Reduction.
Yes. Okay. So either you check your oxidation numbers, or you've memorized the note card, and the note card says reductions in acid solutions. And this is a reduction. So therefore, the other half reaction must be the oxidation, correct? You're oxidizing tin to chloride. So as a student, right, you're not supposed to know which one. I never taught you anything about these, did I? I didn't say there's a special procedure for chlorides. I didn't say there's a special procedure for tin. I just gave it to you, and now you have to deal with it. So what you need to recognize is that because it's a solution, you don't have to write this out on a test. That means AQ, what really is happening is floating in a beaker, there is Sn plus 2 AQ plus Cl minus AQ. That's what this means when it's a solution. So now you're going to choose, do I oxidize tin or do I oxidize chloride? So watch, Sn plus 2 or Cl minus. Can you oxidize tin? Tell your group. If so, then what does it go to?
+4.
Yeah, it can go to +4. Tell your group, can you oxidize chloride?
Yeah, it's the Cl2.
Yes, because it can go to Cl2. All right, look at the slide before. What did it say? When you have a choice, the metal always gets oxidized. Do you see how you had a choice? So then you have to choose the Sn plus 2 as your oxidation choice because the metal gets oxidized. All right? So this, essentially, is what it all looks like. These are your reactants. These are your products. But do you see how I came up with it? I chose to do that based on all that other information. So you know that you need to use the special procedure because it says it's an acidified solution. You know something special about permanganate. But what else do you see when you look at this reaction? How else do you know you need to use the special procedure? It's impossible to balance. There's no oxygen over here. So I will give you this kind of stuff on a multiple choice. I give this to you already done. Today you're going to see that. I'm going to give you folders with the reaction already written out. And then I'm going to ask you to balance it. So you would just have to use the special procedure. You don't even have to do it. So some of them you will have to write out. Some of them you'll just do the special procedure. All right, so first thing we're going to do is we're going to write out the half reduction. Which one's the reduction? Permanganate going to the Mn plus 2. All right, so step 1, we wrote our half reaction. So we're following the steps right here on this sheet. So girls that were absent, it's literally you follow it step by step to figure out how to do it. Balance all atoms for oxygen and hydrogen, except for oxygen and hydrogen. Is manganese balanced? Yeah, that's so important that you check that. Today when we do the folders, you're going to see some of you are going to miss that step, and then everything will be wrong from that point on. You have to balance your atoms first. All right, step 2, we already are balanced for manganese, so we're just going to skip that. You don't have to write that again. What do you do step 3? Balance oxygen by adding. Okay, how many H2Os do I need to add and to which side? Don't call out. Don't call out. All right, do it yourself. All right, look up here. You got that? Okay. Step 4. Add H plus to balance for hydrogen. Go ahead and do that in step 4. When you're done, check up here. So did you add 8 H pluses? Okay, this is the step where students often make a mistake. And I think last block we sort of were doing it perhaps jokingly, perhaps not, but every time someone made this mistake, I verbally pointed it out to the entire class. Not to make anyone be embarrassed, but I want you to see how frequent it happens. It happens so frequently. So you can avoid this happening by checking your electron's charge. So when you need to check charge, you don't look at oxidation numbers. When you want to know your overall charge, on the left and the right, you take the coefficient and you multiply it by the charge. And then your left side must equal your right side. That's how you add electrons. That's how you check for overall charge. All right, so how many negatives do I have on this? 1, right? 1 negative, -1. What's the charge on this? +8. What's the overall charge on this side? +7. What's the charge here? +2. 0. Overall charge on this side? Okay, we have to add electrons somewhere. Without even looking at this, where do you have to add them? To the left. Why, Blue? Why? Why do I have to add them to the left? Because it's a reduction. And reduction means Leo says GR. And GR means gain electrons for reduction. So by default, they have to go to the left, okay? That's one way to tell yourself where they go. The other way, right, is to look at the charge on each side. 7, positive, +2. I need them to be equal. Electrons are only negative, so you can only take away from something. So if this is a 7, I need to add what? 5 electrons to the left to make it a +2. If I add 5 electrons to this, it'll make it a +2. So everybody add 5 electrons in step 5. All right, so that's the last part. Now we're going to go on to the oxidation half-reaction. Everybody see that? All right, second part should be easier. Our oxidation half-reaction is just what? Correct. Sn plus 2 goes to Sn plus 4. Are your atoms of tin, are they balanced? There's no oxygen, there's no hydrogen, so the only thing that you need to do is what? Add electrons. How many and to which side? Try. When you're done, look up here. Give me a humble thumb. What's a boasting thumb? A humble thumb. No humble thumbs back there? Matt, you got this wrong? He's so humble, he wouldn't even put his thumb up. Did you guys get it in the back? Yes? Okay. No, that's a little boastful. Easy on the thumb. All right. Apparently I say thumb funny. I don't know if I do. Do I? Years ago, someone said to me, please stop saying thumb. And now I'm conscious of it. Sort of like that time that Grant pointed out to me that I put my hand behind my back. Was anybody in here, that class? So apparently when I write, I put my arm behind my back. Did you ever notice this? Yeah. So one day he said it to me, and I was like, why would would you ever say that? Because now this is 2 years later, I'm still conscious about putting my hand behind my back. Okay. So now we have to cancel our electrons by using least common multiple, right? What's the least common multiple of 5 and 2? 10. So I multiply the top by 2 and the bottom by 5, and then I combine by canceling my electrons, and then we'll look at this when you write this all out. So we get to the last step here, which is combining them, and then you end up with the final reaction. So you all see that in your slides? All right, so this is what you need to do at the end. If you want to walk out of the exam on Tuesday feeling completely confident, you check your work. You'll know if it's right if your atoms are balanced and your charge is balanced, and then you'll be like, yep, I aced this. If you don't check your work, then you have no idea if you did it right or wrong. So you check atoms first, which is like honors chem style. 2 manganese, how many? 2. Oxygen? 8. 5 tin, 5 tin, 16 H+. Okay, charge is not as simple. A lot of times people forget. So how do you find overall charge? Coefficient times charge, right? It's not oxidation number. It's coefficient times charge. So 2 times -1, what's this one? What's the overall charge? Come on, where are you, Lou? Jump on it. Positive 24. What is this one?
+4.
Plus 4.
+20. 0.
Yep. So they're balanced. You get it? You check it, you'll know that you got it right. All right, next one. Sometimes you'll be given a reaction in which you're going to do the special procedure, and it doesn't say something about being acidified or not. You'll just know you have to do it because if you don't have the ability to balance it, then you do the special procedure, right? Like remember, if you're trying to go back and forth and it just doesn't balance, you'll use this. So you can always add water to balance for oxygen. You can always add H+ to balance for hydrogens. So this question appeared on the 2009 AP exam. Literally this sentence with this reaction. It says, write the balanced oxidation half-reaction for the decomposition of hydrogen peroxide. Could you do it if that was your question? So I just want to point something out to you. A half reaction is not the whole thing. So sometimes, and I in fact give this question later on in the year, like in a different section that we're in, just to kind of remind you about this. And sometimes students will get it wrong because they try to write out a whole reaction. It's not asking for the whole thing. It's asking for a half reaction and just the piece that's oxidation. All right, it's weird to you because all you have is one reactant, but you should already know when we do disproportionation reactions, that was fine if we only had one reactant, right? If we only had Fe+2, no big deal. We can go to the +3 and to the 0 state and we would be fine. So you can have one reactant. It's going to be both oxidized and reduced. So how do you know which one's the oxidation and which one's the reduction half-reaction? How do you figure that out? That's what you do. If you don't know what gets oxidized and you don't know what gets reduced, you write out your oxidation numbers and you figure it out. So everybody write your oxidation numbers down on here. Once you do that, you can figure out which one's oxidized. So what's the charge on oxygen here? Oh, see, there's discrepancy. If you said -2, you're wrong. Why? Because it's peroxide. And that's always the tricky one, right? So this is -1, -2. This must be +1 to give me the +2. So these are my oxidation numbers. Now it's -2 +1 +2, 0. So what is hydrogen doing? Anything? Nope. Hydrogen's not being oxidized or reduced. It goes from +1 to +1. Oxygen is being both oxidized and reduced. So this to this is the reduction. This to this is the oxidation. You still don't get it? Why? Did you write your charges?
Yeah.
But incorrectly? So if you wrote this as a -2, then it wouldn't make sense to you. You would only have an oxidation. You wouldn't even have a reduction.
I get like the writing the part like the oxidation numbers, I don't like applying it. Like,
So if your oxidation number goes up, it's oxidation. And if your oxidation number goes down, it's reduction. And that should make sense because we know that if something's going to get reduced, it goes down, right? Like in general in life. I feel like you guys were absent for that lecture. So if an oxidation number goes down, it's reduced. If an oxidation number goes up, it's oxidized. That's it. So here it is, -1, and then it goes to a -2. Is that down or up? Down, so it's reduction. -1 goes to a 0. Is that down or up? Up. So then it's an oxidation. So then the oxidation is H2O2 goes to O2 because it specifically says write the oxidation half-reaction. Didn't ask for the reduction, it asked for the oxidation half-reaction. All right, so on your own right now, I want you to try to balance that using our special procedure. But realize it didn't say anything about acid. We still can use the procedure. All right, so let's check. So you have step 1 is the H2O2 goes to O2. We already have our atoms balanced in a sense because there's no other ones. So we have to immediately go to the oxygen. There's 2 oxygens on the left, 2 oxygens on the right, so oxygens are already balanced. There's 2 hydrogens on the left, but I need 2 hydrogens on the right, so I add 2 H+. What's the charge of the left? Zilch. What's the charge of the right? +2. This is an oxidation, so that means that your electrons need to be on the right-hand side anyway. How many do you put? 2. Humble them. Okay. Basic solutions. If something is basic, it has OH in it. Agreed? Right? Bases have OH. Acids have H+, right? So I can't tell you, if I have a basic solution, you know you have to use a special procedure, but look at the reactions that you've just done in the past. What's in the final reaction? That shouldn't be there if it was a base. What do you have back here in the final reaction? H+. What is H+? An acid. So if I tell you a base, then you can't possibly have H+ sitting around in there, right? The bases, don't feel like, oh my goodness, we're starting a new topic and then we're going to have to know more information. The bases are going to be the exact same procedure as the acids except for one extra step where we add OH at the end. The only extra thing that you have to really memorize is one reduction, okay? One reduction is this one. I wrote it. It's up there. It's the same permanganate that gets reduced in acid solutions. It's just that the product is something different. So permanganate would be with a group 1 metal, like potassium permanganate is pretty much what they always choose. And by the way, potassium permanganate, does anybody know what color it is? Beautiful purple color. It really is a pretty solution. So permanganate in bases goes to MnO2. All right, so this is a simple multiple choice question that I'm going to give you on your test. I'll give you this, and I'll say the oxidation number of Mn goes from what to what? Try it. The oxidation number of manganese goes from what to what? Try. So we're going over here to Tristan. What's the charge of manganese on the left side?
7.
Why?
Because oxygen's -8, and I need to have -1 negative.
Yes. Good. All right. Tori, what's the charge of manganese on the right side?
+4.
Oh, no. It becomes +4, right? It's minus, oh, it is. I'm the worst. I'm so sorry. And this time you're right, and I'm like, nope, nope. I was just checking, testing you guys. Sorry. Yes, Tori, you're right. 100% right. Okay. That's a really simple question, isn't it, to get on a multiple choice? You will get simple questions on multiple choice. You don't want to mess those up, okay? Really pay attention to some of the details. All right, so we're going to memorize this now as one extra note card that you're going to bring in tomorrow. And it's the same exact thing that it will do if it's in an acid solution. So if this is the reduction, you will oxidize P and D block metals. You'll oxidize the sulfite, but there's no peroxide in here. But see all of the ones written on the front. For the oxidations in acid, you can still use the same oxidations in base. Okay? So the only new thing would be to memorize the new reduction of permanganate. You know I'm going to check that, right? Yes. Okay, so I look at this sentence, and how do I know what to do with it? Clue number 1, basic solution. And then, do I know what to do with the magnesium sulfate? You may not. You might, though, because you memorize the note card, and you know that sulfites get oxidized to sulfate. So if you memorize the note card, then you're ready for it, but you're probably going to be familiar with this permanganate thing. Because it's in a basic solution, you're doing MnO4 minus goes to MnO2. And then your sulfite gets oxidized, right? Let me see, pretend I was you. A solution of magnesium sulfite. And maybe you didn't memorize your note card. Maybe you didn't force yourself to remember that SO3 minus 2 gets oxidized. How could you oxidize magnesium? You can't. There's no other charge for magnesium. You can't go up. So then by default, it has to be the sulfite. And sulfite goes to sulfate because you're going to memorize it. So then this is your product. So you're going to have to do that special procedure and use the half-reaction method. So I'm going to leave you guys to it. I want you to go all the way until you get to step 7 and stop there, and then I'll show you what to do. All right, let's check these. So you get to, hopefully, all the way down here, and you should have 3 electrons. And if you didn't get 3, it's likely that you didn't add your charges. This is a -1, this is a +4, so this entire side is a +3. This entire side is 0. You had to add 3 electrons to reduce that down to 0. On the other oxidation of sulfite, you have 2 electrons being lost. Now you have to use least common multiple. You all should have gotten to this point, and then I asked you to stop for number 7. When you combine your half reactions, we all know that we need to just cancel our electrons, agreed? But what you need to really do is cancel everything that can be canceled. So do you see how many hydrogens are here? 8, right, on the left. How many hydrogens are here on the right?
6.
So those go away. 8 minus 6 H pluses gives me 2 H pluses on the left. On the right, what do you notice that can be canceled from the left and the right? Water. 3 waters on the left, 4 waters on the right. This goes away. 4 minus 3 waters gives me 1 water. So I'll have 1 water left on the right. And then everything else will come down, just like you've done before. So take a look. So you're just making sure that your H pluses and your waters match, but then everything else is just directly brought down. So if this were the acid solution, we would be done. We would stop. We would check our charge, we would check our atoms, and we would confirm that we're correct or not correct. But when it says base, we have to do one more thing. So what do we say? Bases always have what? OH. Acids have H+. See how this has H+ in it? So this would be, yeah, this is great if it were an acidified solution, but it's not an acidified solution, it's a basic solution. So you have to add, final step on my little sheet says, I hand wrote it in, it says, for bases, add OH minus to cancel H+, right? And then exclamation, exclamation, due to both sides. So if I have my two H pluses here, how many OHs do I need to add? 2. So we're going to add 2 OHs to the left side. H plus OH minus makes water. How many waters am I going to make? 2 waters. Because you're technically making 2 HOH. And HOH is water. So as soon as you add the OH, you're doing that to make water. To get rid of the H plus and make water. Once I do that to this side, I have to add it to this side. So you're going to add OH minus to the right side. It's already written for you. Now you need to simplify it again. I have 2 waters on the left. How many waters are on the right? So now this one's going to go away. I'm going to subtract out one of these waters, and I'm going to be left with only 1 water on the left. Oops. My computer died. But I bet you can figure out what it was. Just combine it. Everything that was there before, and now all you have is 1 H2O on the left. I'll write it out for you. And then 2 OHs on the right. So, let me find it and I'll finish it up for you. So you should have 2 MnO4 minus plus 3 SO3 minus 2 plus H2O yields 2 MnO2 plus 3 SO4 minus 2 plus 2 OH minus. Yes? There it all is. Done. The remaining 2 slides talk about titrations, which I will talk to you about tomorrow. But for the remainder of class, we're going to practice this.